Now, last class I was talking to you, or I was teaching to you about emission and absorption spectra. In there itself I taught you, that is hydrogen spectrum I taught you. I taught you hydrogen spectrum. Now, in the hydrogen spectrum I said you that we are having the different series. Got it? And I also said you that instead of hydrogen, if you use any other element having higher molecular mass, then you will be getting a complex spectrum you will be getting it. Whatever it is, in the hydrogen spectrum we have studied Lyman series, Balmer series, Paschen series, Brackett series, Pfund series, and after Pfund there are infinite number of series are there, which is altogether called as Humphrey series. Now this name was given according to the name of the scientist who discovered this particular series, so to say. Alright, now in this what you can say, in this series, as you saw, that Lyman is coming under the ultraviolet spectrum, Balmer is coming under the visible spectrum, then Lyman, Balmer, Paschen onwards, all it comes under the infrared spectrum, we can say Brackett, Pfund and all those things. It comes under the infrared spectrum. Now, Rydberg was a scientist. He gave a formula. Rydberg formula. He gave a formula, alright, to calculate the wavelength and the wave number of the spectral lines in the hydrogen spectrum, we can say that. What I said, Rydberg was a scientist who gave us a formula to calculate the wavelength, the wave number of the spectral lines. Spectral lines means Lyman, Balmer, Paschen, Brackett, Pfund, all these are the spectral lines. Alright, they are the spectral lines in the entire, what you can, the spectral series. What spectral series? The hydrogen spectrum. Alright, in the entire hydrogen spectrum, alright, he gave us a formula to calculate the wave number and wavelength or whatever it is you want to know. So what is that formula? That is nu bar is equal to R 1 by N1 square minus 1 by N2 square whole into Z square, we can say that. Where R is your Rydberg's constant, where R stands for Rydberg's constant and its value is 109677 centimeter inverse, we can say that. 109677 centimeter inverse. You can convert it into meter inverse also. You know that how to do it in the meter inverse. So in this way, what you can say is that he used this particular value, that is a Rydberg's constant, and by using this formula, we can calculate the wave number of the spectral series. It's a wave number. And what is wave number? I said you, wave number is the reciprocal of wavelength. So once you know the wave number, alright, that is nu bar, we can say that we can calculate the wavelength also. In this way, as I said you, we can calculate the wavelength or the wave number. Now comes N1. N1 is the lines of the lower spectral series. Alright, it is the lines in the lower spectral series, we can say that. And N2 is the lines in the higher spectral series. For example, let us say, for a given spectrum, alright, it's a spectral series, mind it, the given spectrum, and these are the lines, we can say that, Lyman, Balmer, Paschen, Brackett, Pfund, we can say that. So, in that particular, what you can say is that N1 remains always constant for a particular line, we can say. N1 remains always constant for a particular line, we can say that, or for a particular spectrum, we can say that. N1 remains always constant. Now, what does it mean? For example, we start from which series? Lyman series, from the bottom, na? Lyman. So, N1 is 1 and N2 is, it can be 2, 3, 4, 5, ... That's it. So, this is for which particular kind of series? I said you, Lyman series. Similarly, for Balmer series, N1 is again, it is constant, that is 2. N1 is 2 and N2 is 1 higher, that is 3, 4, 5, 6, 7, ... That is for which series I said you? Balmer. Alright. So what you find now for what you can say Paschen, we can say that Paschen series. So what you will find is that I am writing it here, N1 is equal to 3, N2 will be how much? 1 higher, 4, 5, 6 in this way. Alright. So what you find is that for a given, what you can say, line or for a given spectrum, the lower spectral lines always remains constant. The variable is the higher one, the N2. So hence I said you N1 is a lower spectral series and N2 is the higher spectral series. But you can say lines in the higher spectral series. Again I repeat, N1 is a line in the lower spectral series and N2 is a line in the higher spectral series. So if for Lyman series, N1 is always 1, N2 will be 2, 3, 4, 5 in this way. After Lyman comes Balmer. Balmer, N1 is 2, N2 will be 2, 3, 4, 5, 6 in this way. One higher. Got it? Now for Paschen, N1 will be 3, N2 will be 4, 5, 6 in this way. Bracket, Pfund, Humphrey, in this way it will go on. Got it? So in this way what we find is that for a given, again I repeat, for a given line in the spectral series, N1 remains constant, N2 is variable. Got it? Now as it is variable, we are also having a limiting line. We are having a limiting line. What is that limiting line? You can write down the definition. The limiting line of any spectral series in the hydrogen spectrum where N2 is infinite. What I said? The limiting line of any spectral series in the hydrogen spectrum is the line where N2 is infinite. The value of N2 will be infinite. So in the Rydberg's formula, in the Rydberg's equation, N2 will be infinite. When N2 is infinite, N1 cannot vary well. When N2 is infinite, that is known as the limiting line. Again I repeat what I said. The limiting line of any spectral series in the hydrogen spectrum is the line where N2 is infinite. We can say that. That is known as limiting line in the Rydberg's formula, so to say. So in this way, what you understood here, by using the Rydberg's formula, we can calculate the wave number, we can calculate the wavelength which is unknown to us. And what does Z stands for? That you know it. Z is the atomic number. For example, in case of hydrogen, the atomic number will be 1. Got it? Hydrogen atomic number will be 1. For helium, atomic number will be 2. For lithium, atomic number will be 3 in this way. But we do not say helium, lithium according to the name. We say as hydrogen-like particles. You know what is that? Hydrogen-like particles. Now listen carefully here. Hydrogen atomic number is 1. We know that. If I write He, that is nothing but plus, then what is the number of electrons now present in helium? Number of electrons now present in helium is 1 only, because helium is having atomic number 2. When I write He plus, 1 electron. When I write Li2 plus, what is the atomic number of lithium? 3. But when I write Li2 plus, then what is the number of electrons now? 1 only. Got it? So in this way, He plus, Li2 plus, they are known as hydrogen-like particles. You will be getting this term in your book in the numericals. Hydrogen-like particles. So they are called hydrogen-like particles. You know why it is? I have to explain to you. Because when atomic number of hydrogen, atomic number I need to write here. This is the mass number I have written. So atomic number of hydrogen is 1. Got it? Atomic number of helium is 2. No doubt. But when I say He that is plus, then how many? What is the number of electrons now there? 1 only. When I say Li2 plus, even if the atomic number of lithium is 3, but what is the number of electrons there? That is 1 only. But while using hydrogen, the atomic number will be 1, because Z stands for atomic number. Z now stands for number of electrons. Understood? If it is He plus is being used, then hydrogen-like particles, then Z value will be 2 only. Alright. Now if lithium is used, Z value will be 3 only. They are called as hydrogen-like particles. Mind it, they are called as hydrogen-like particles. He plus, Li2 plus, but its atomic number you have to use it. Nah? You can't use atomic number as 1. Alright. If its atomic number is 1 you are using, then it is hydrogen only. Alright. They are known as, this is hydrogen-like particles. Find it? Okay. This is about your Rydberg's equation or Rydberg's formula, which I say you. Now a lot of numericals is there to be done. When we do the numericals, you will come to know. The more things will be clear, because these are all numerical things. Once you do the numericals, then only the things will be clear to you. Now, after that, we will come to, that is Bohr's atomic theory. I said you, after Rutherford's atomic model, after the drawbacks of the Rutherford's atomic model, I said you, before the development of the Bohr's atomic theory, lot of development was there in between. Because Rutherford's student was Niels Bohr. So a lot of development took place. What was that? We got the electromagnetic wave theory. After electromagnetic wave theory, we got the Planck's quantum theory. Then after that, we came to know about emission and absorption spectra and the Rydberg's equation we came to know. Now we will come to the Bohr's atomic model. Alright, we will come to the Bohr's atomic model, so to say. Now, next is, before going to the Bohr's atomic model, just let me remind you what Rutherford said, what was the drawbacks of the Rutherford's atomic model. Now, Rutherford said that electrons is moving around the sun, just like electrons is moving around the nucleus, just like the planets is moving around the sun in the solar system. That means he compared his atomic model to the planetary motion of the sun, which Maxwell pointed out that it is not possible. Maxwell said that the sun, moon, earth, these planets, they are these heavenly bodies, they are neutral particles and they are macro particles, bigger, quite bigger. Whereas electrons, protons, neutrons, they are the charged particles and they are micro particles. So it is no comparison, first of all. Second point, he said that when the neutral particles is moving, there is no loss or gain of energy. Like the sun, around the sun, the planets are moving. There is no loss or gain of energy. Alright. Similarly here, but not similarly, rather I should say, but when the electron is moving around the nucleus in an atom, electron is a charged particle. There is always loss of energy. Why? Because when the electron is moving in a circular path, any charged particle moving in a circular path is liable to lose energy. It is liable to lose energy. Why? Because when a body is moving in a circular path, the angular velocity is changing. Angular velocity is changing. I have explained to you earlier all these things. When the angular velocity changes, the acceleration also changes. Angular, got it? That is acceleration changes. Due to which energy is released, and as the energy is released, the path gets shorter and shorter. Alright, the path gets shorter and shorter. Let us say this is your nucleus, which is positively charged. The path is getting, now this is your electron. Alright, it is moving around the nucleus. It is losing energy. The path is getting shorter and shorter and shorter. And ultimately what will happen is that it will come nearer to the nucleus and it will fall into the nucleus and it will get destroyed. That Maxwell suggested us. Maxwell suggested us that any charged particle is moving in a circular path, alright, it is liable to release energy, it is liable to lose energy. And remember that this path is made up of energy level. It's not made up of bricks or concrete or something like that. It is energy level. So energy is losing means the path is getting shorter, smaller. And when it comes closer to the nucleus, what happens? The electrons falls into the nucleus and it gets destroyed. And to happen this, for an electron, Maxwell calculated it that the time interval is 10 to the power minus 8th of a second it takes one electron to come to the nucleus and it will fall into the nucleus and get destroyed. It takes 10 to the power minus 8th of a second, we can say that. So he told us that if we calculate the number of electrons which is present inside the earth, let us say there are some millions of electrons which is present inside the earth, and each electron is taking 10 to the power minus 8th of a second on an average. Nobody has calculated, on an average we can say that it is taking. So you multiply with a million of electrons, you will be getting some seconds, few hours for the earth to get destroyed. If we consider that whatever Rutherford said is correct, if we consider, let us say, Rutherford suggested that just like the planets is moving around the sun, similarly electrons are also moving around the nucleus in this particular manner. For the timing, let us consider what Rutherford said is correct. So the earth is having the charged particles, these electrons and all these things, you know that it's having. So this particular, if one electron is taking 10 to the power minus 8th of a second and it is falling into the nucleus and getting destroyed, then it will take few hours for the earth to fall into the sun and get destroyed. So we cannot compare this. It's not possible, isn't it? It's quite absurd. Got it? Whenever this Maxwell put forward this theory in the 18th century, so to say, and today is 21st century, we can say that. So many years has passed on and nothing has happened. So definitely we cannot consider this particular theory. So it was completely discarded. I hope you understood. It is completely discarded, this particular theory. Clear? So it is not possible that the electrons is moving in a circular path. The Maxwell proved this particular thing. It is not possible because any charged particle moving in a circular path is liable to lose energy and it will fall into the nucleus and get destroyed. And hence, this theory we cannot put what you can say in terms of nucleus, electrons, protons. We cannot compare it with the planetary motion of the sun. We can say heavenly bodies. And moreover, he was not able to explain the line spectra. Got it? He was not able to explain the line spectra, Lyman, Balmer and all these things. We can say that. And he was also not able to find out the energy of an electron. That what is the energy possessed by an electron, whether it is stable or unstable, because energy is inversely proportional to stability. So if you are not able to calculate energy, you cannot calculate the stability of an atom. So he could not say anything about all these things. So hence his theory was discarded. So his student, that is Niels Bohr, he came forward with this particular theory. What is that? We'll see it.